Okay, this video lesson is dealing with all the gas laws most of the gas laws that you'll encounter with gases, obviously. Okay, so the first one we're looking at, and would be a summary sheet. We've got about 4 different gas laws, 3 gas laws, and then we'll combine them all to form the combined gas law. As you know, we're very creative in chemistry when it comes to naming things. All right, so the first one is Boyle's law. So I'll give you a few seconds to just copy down Boyle's law. Briefly, okay, it's an inverse relationship. It looks a lot like the dilution formula, where we have 2 sets of conditions, okay? And also, in this case, it is multiplication. So we're multiplying these 2 together, the first two conditions, so pressure and volume, and then that should equal the pressure and volume, the product of the pressure and volume for the second condition. This is all as long as the temperature remains constant. And also the number of moles of gas. Okay, something that we have to kind of consider as well. But generally, in most problems when we're dealing with them, they won't necessarily state that. But if there's no change, if it doesn't see that there's a change in the temperature, then or the number of moles, then we'll assume that it isn't changing at all. It's just the volume, the pressure that are changing. Okay, so it's an inverse relationship. If you're to measure several pressures or volumes of gases and then pair them up with their pressure, we would see this kind of relationship. It's very much like a reciprocal graph, okay, or a where it's a hyperbola, okay, and so the pressure as the volume decreases, okay, the pressure will increase, okay, so wrong way I was going there. So if the volume decreases, the pressure goes up, okay, and if the volume increases, pressure goes down, okay. And one of the demos that you'll have a chance to take a look at is taking a look at the pressure when in a syringe with a marshmallow that's present in the syringe, okay, and you can really see what's going on. Okay, so that's the relationship, that's the formula we're going to use. Okay, so let's take a look at this first example. Okay, so Boyle's law says basically, what is the volume of a 4.8 liter solution, 4.8 liters of hydrogen gas? Okay, so we're just going to identify all the important stuff here. If the pressure exerted on it increases from 55 to 127, okay, and assume that the temperature remains constant, okay. The question is, what is the volume? What's the volume? All right. So we'll set it up just in the same way that we did with those dilution problems. Okay, so we'll have an initial and a final, or a first and a second. Okay. So we want to know what the new volume is if the volume starts off at 4.8 liters, okay, and it increases from, what's the 1 here, 55 kilopascals all the way up to 127. That's the only little tricky thing, is you got to really be paying attention to the language that's used, okay, and it says it's starting from, so that has to be the initial condition, okay, and it's going to, it increases during this time to 127, okay, so that's what the volume's looking for, okay, so that's our question, okay, we sub all this stuff in to our formula and we can get our answer, okay, so starting off with, and we might want to use the GREAT method, so given, required, so we've got that, we're going to use an equation now, get the answer, and then finish it off with a therefore statement. Okay, so that's what the GREAT method means. Okay, so now we're going to do our equation. So P1 V1 equals P2 V2. Okay. Now what we'll do is plug everything in. 55. I like using the units. It just reminds me that if they're not in the same unit, we will convert them, okay, to have the same unit, where you have a match between the quantities. Okay. We have two pressures. Those have to be exactly the same. The volume, it doesn't matter what it is. There's no specific requirement. Okay. Now what we're going to do is rearrange. Okay. We want to get the volume. So we need, this is multiplication. We're going to divide. So 55 kilopascals, 4.8 liters, 127 kilopascals. Okay, divided. The kilopascals cancel because they're found on the top and the bottom. Okay, and now we can just sub this in, type it into our calculator all at once, and we get 2.08, and that's liters that we're looking for here. Okay, the liters is the only unit that's left over. So what's happened here is, does that make sense? Well, the pressure's gone up. Okay, so it's increased. So volume's got to do the opposite. That's the key thing with these, with Boyle's law, is it decreases. And the volume did decrease. And it went down by half because the pressure went up roughly by by double. Okay? Great. So try the next problem. Okay. I'll leave a little bit of time. Okay, and here's the answer. Okay, again, we've identified all of the important information. Will the volume increase or decrease? And what will the new volume be? New volume. And will it increase or decrease? So the volume has increased. Okay, very similar type problem. Could have also done one with where we're trying to find the pressure in that case. Okay, so that's Boyle's law in a nutshell. Remember that formula, and that it's all multiplication. All right, this one's the most is the simpler one of all the laws because it is dealing with multiplication. So the next law that we're going to look at is Charles's law. Now this one kind of makes sense. We're going to use the balloon on a hot plate attached to a flask to kind of demonstrate this. But basically, as the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. Okay, pretty straightforward. Okay, it kind of makes sense because as the temperature goes up, there's more particles. The particles are moving faster. Okay, so if the pressure doesn't change at all, okay, those particles can now push a movable side of one of the containers, can actually increase that volume or push with greater force and increase the volume of the sample of the gas. Okay, it's a direct relationship. It's the opposite of what we saw there. Okay, so if we were to graph it, okay, we would see something like this. Okay, where it's going up linearly. Okay. The only problem is it's got a vertical intercept, okay? And so as a result, it's not directly related. It is partial variation, okay? And so in order to make it directly related, so we have a nice little formula where we don't have to have an intercept in there, what we want to do is go back and start our axis here, which is the temperature, the lowest possible temperature that we can have, which happens to be 0 Kelvin or absolute zero. Okay, so we adjust our scale to absolute zero. This is actually how they knew that there had to be some final lowest temperature you could ever go to. Is looking at this law. So we're looking at gases around room temperature, and they were able to deduce that there had to be some even lower temperature, but a final temperature that you can never go below. Technically speaking, that's the temperature when particles are moving the slowest, or not moving at all, but that's not true. We know that particles will always move but they're moving at their very possible slowest temperature, okay? Slowest speed, I mean, okay? And it's the lowest temperature present, because that would be the average, basically, of the speeds of the particles would be 0, okay? But it's not quite 0. It's the lowest value that it could be, okay? So we do need to, with all of the temperatures, we always have to change it to Kelvin, okay? So it's a simple little change. And because it's directly related, it's not going to be a product anymore like the Boyle's law. It is going to be a ratio, okay? And what you're going to want to do is you're going to want to set it up. I prefer using it in this format. You want to set it up so that the left side's all the initial conditions, the right sides are all the secondary conditions, okay? And then, because it's a ratio, I would cross multiply with the numbers present in there. And you end up getting this relationship, okay, where the temperature and the volume are mixed together. They're from two different conditions, okay, when they're being multiplied, okay, and it just helps it be parallel as well. Remember, this is dealing with we're dealing here with constant pressure and moles of gas. Okay, so we're not going to increase the number of moles, nor are we going to change the pressure at all. Okay, so let's look at our example for Charles's law. Okay, so Charles's law. So for Charles's law, okay, do the same thing. We're going to highlight all the important stuff. So we've got 50 centimeters, and again, you can do a lot of this stuff without even thinking. 50 cubic centimeters, temperature's going from 15 to 50. What's the new volume? Okay, so again, initial and final. I like organizing it this way. So my initial volume is 50 cc's. Initial temperature is 15. We're going to add 273. I don't like leaving it as Celsius at all. You could put in Celsius in there. It's just going to give you the wrong number. So don't do that. So 288 Kelvin. And then the temperature is going up to 50. Again, change it right away. 323 Kelvin, and then the volume is what we're looking for here. This is a direct relationship, so we know that it's going to increase. Okay, so what's the new volume? Calculate the new volume. That's our new volume there. Okay, I like setting it up this way because it reminds me that we keep everything on the left together for the same conditions, and on the right together. So I'm going to plug everything in, 50, and I use cc. It doesn't matter. It could be centimeters cubed, written out completely. That's all that is. It's also milliliters too. We don't know what the volume is, so 323 Kelvin. I like using the units again as well. Okay. Different ways that you can do this. I'm going to show you a couple different ways. This one's easy because it's just a simple division. So what I'm going to do is I'm just going to multiply. So 323 Kelvin, 50 cc, 288. You want to be careful if you're calculating temperature, because if you just do that simple moving over, you're going to end up getting the reciprocal of the volume, not the actual volume. Okay, so careful with that. Okay, so the kelvins are gone. I'm left with cc's. 3 divided by 292, 88 times 50. You can do it in a couple different orders. And my new volume is now 56.1 cc's. Okay, therefore the volume is 56.1 centimeters cubed, or cc's. Okay? And does this make sense? Well, the temperature did go up, so it does make sense that the volume went up. Okay? It's a direct relationship. All right. I want you to try the next one. Do the same kind of thing. I'll let you go ahead. So I pause the video there now. Okay, coming back to the video, what we're going to do is I've set up my all my givens and what I'm looking for. Again, I'm looking for volume here. I've changed the temperatures to Kelvin. See, if I would have used the Celsius temperature in these, I would have got a negative volume, which should be like a clear indication that you made a mistake. Okay, so be very careful with this. It has to be in Kelvin. Okay, here I've done this a little differently. I've set it up. I've cross-multiplied because that's what you're going to want to do if you have a variable down in the denominator. Okay, you'll be finding the reciprocal of the temperature I meant to say earlier. If you do this incorrect, if you don't follow this step, or if you're not really watching what you're doing with the math. Okay, so I cross-multiplied this time, so 1.2 liters times 258 I put over here. These two guys, 288 Kelvin times the volume. I'm going to divide by 288, okay, and I end up getting a volume of 1.075. I rounded it to 3 significant figures. And so the volume is 1.08. The volume went down. Does that make sense? Well, yeah, the temperature went down, so the volume should go down. Okay. So next law, the next named law, law that's named after the scientist that we're studying it, is the Gay-Lussac law, or Guy-Lussac law, whichever it happens to be. This one is almost identical to the volume, or Charles's law. It's the same relationship. As the temperature goes up, the pressure goes up, as long as the volume stays constant. So volume and moles of gas is constant. Okay? So again, it should look a lot like that graph. If we had a graphical representation for the Gay-Lussac law, that's what we would see as well. We could have figured out what the absolute temperature was. Okay? And remember, you could cross-multiply and get a slightly different version that looks like this for the Gay-Lussac law. We're just going to leave it like in that example, leave it in this format, because all the first condition variables are on the left and the second condition variables are on the right. Okay? So again, we're going to take a look at an example. So we have it here. So Gay-Lussac's law. At a temperature of 10 degrees, the pressure is 225 kilopascals. What happens if the container reaches a temperature of 42? Okay. Now, the temperature in Celsius here has gone up by a factor of 4. That's, if it was directly related by Celsius, that would mean the pressure goes up by a large amount. But it's based on the Kelvin values. So as a result, this pressure change won't be that huge. Okay, so just be aware of that. So again, we're starting off with temperature 1 is 10. I'm going to add 273 right away. So 283 Kelvin. And then the pressure, 25 kilopascals. The temperature is 42. Add 273. Turn it into Kelvin right away. 315. And we're trying to find out what this new pressure is. Okay? What will the pressure be? Okay? All right, so we're going to plug in our formula. So again, great method. We've got our required. We know our givens. Now what we're going to do is figure out our, use the right equation. So P1 over T1 is equal to P2 over T2. Okay? Plug everything in. And these can be written upside down as long as they match. As long as those pressures are up on the numerator and temperature on the bottom. We could flip it. We're going to have temperature on the top and pressure on the bottom. Depends on what you're trying to isolate. Okay, so kilopascals all over 283 Kelvin is equal to the new pressure, which we don't know, 315 Kelvin. I'm going to do this one in the simple format. Okay, this is down on the numerator. It's being divided, so I'm going to multiply by 315 Kelvin. Okay, these guys will cancel, and then all I have to do is multiply here, and I get my new pressure. So 315 times 225 divided by 283, 250.4 kilopascals. So the pressure has gone up, increased, because the temperature increased, but not by a ton. Okay? So that's my answer, and then my therefore statement. Therefore, the pressure is 250.4 kilopascals, which is increased. Okay? Let you do the next one. Try the next one. Pause the video, and then we can take a look at the answer. Okay, so this temperature has really changed quite a bit. Okay, so we're going to see a large change here, but not as much as we think it is if it was proportional based on Celsius. Again, we have our two sets of conditions. We've written out our equation. Okay, plugged in all our values. This time I've cross-multiplied again, so 520 kilopascals times 683. Okay, 298 times the pressure. Okay, I'm going to divide by 298, so that's now over on the other side by division. And I get a final pressure of 1,192. It's gone up by a factor of 2. That makes about sense because the Kelvin temperatures are off by almost a factor of 2. Okay, so therefore the pressure is now 1,192 kilopascals. Okay? We've done our great method. Okay, last law is the combined gas law, and this one just combines them all. Obviously, this is a very straightforward kind of name for the combined gas law. All we're going to do, and this is the one I would memorize if I had to memorize anyone, we're just going to put in Boyle's law and then add in Charles's law to it. Okay? Well, Charles's law is based on volume, so I'm just going to put it divide by volume and temperature, Just going to divide by the temperature. The nice thing about this formula is all of the laws are provided here. We just hide one of the variables where it's constant, where it stays the same. Here we've got Boyle's law. Here we've got Charles's law. Here we have Guy-Lussac's law. Okay? So this one's really useful to us. Okay? So let's try this problem. An aerosol can with a volume of 325 milliliters. It contains propellant at 445 kilopascals at 20 degrees Celsius. Okay? So let's write all this stuff in. Volume 325. The pressure 445 kilopascals. Temperature 12, and I'm changing it right away. So that's going to be 285 Kelvin. Okay, calculate the new volume. So that's what we're doing. If it were allowed to escape at a pressure of 101 kilopascals and the temperature is 21, which is really 294 Kelvin. Okay, so we've got all three variables changing. We're just going to plug them all in, sort it all out, get the final answer. Okay, so we've got our formula already. So 4, 4, 5. Remember, the paired quantities, the ones that have two sets, they need to be in the same units. Okay. We're just showing these more simple versions. Okay. We don't know what the volume is, but we do know what the pressure is. So volume 2, 294 Kelvin. Okay, we could do it a couple different ways. Okay, I don't know what the volume is, so I need to isolate the volume. I'm going to multiply by 294 and divide by 101. That's really all I need to do. So 294 Kelvin. 285 Kelvin. Those are canceling, and then this has to be divided by 101 kilopascals. They're the same units, so they cancel. If they aren't the same units, they don't cancel, so you can't actually get the answer. Okay? We've got everything all sorted out. I'm going to multiply the tops and then divide by the bottoms. Careful with the bottoms, though. You really want to make sure that you use brackets here when you do this. Okay, so I'm just going to show you what I'm going to type in. Okay, so 294 times 445 times. You could calculate these separately and then just divide the two, which is another way of looking at it. But if you do it all at once, you're going to really want to make sure you have a bracket to multiply the stuff down on the bottom together. Otherwise, you're going to mess with the math. It's not going to follow, because the calculator doesn't know that the numerator has to be, like the whole denominator, has to be used as the divisor, okay? So that's going to allow it to happen. Gives me an answer. You'll know when you get an answer and it doesn't really seem reasonable. And this is milliliters. Okay, so the volume's gone up quite a bit. That makes sense. It's an aerosol. It's going from this pressure, large pressure inside the can, and now it's going to take up more space in the room or wherever it happens to be. Okay, so now the gas is going to take up this space. What else does it make sense just like as a real reason, but also does it make sense with the math? Well, the temperature hasn't really changed too much, but the pressure's dropped by a factor of about 4, so it makes sense that the volume would have gone up by about a factor of 4. Okay, and then finish off with my therefore statement. Therefore, the new volume is 1,477 milliliters. Okay, and that's the final gas law, and that's the end of this video lesson.